like to welcome Fino from who got her PhD at Fino in Genova. Genova is is it Bologna or Genova that's the oldest?
Bologna.
Bologna is the oldest.
Bologna.
Yeah. And but she's currently at Florida International University and Fino, and she will be speaking on canonical metrics and complex structure.
Okay. Thank you very much for the introduction and for the invitation. It's the first time here, but also in Texas, so I'm very glad. Okay, my talk will be not real geometry, but complex geometry. And I will try to focus on, let's say, I will explain in a moment what I mean for canonical metrics. So most of the talk will be on non-killer geometry, but some motivation will come from killer. So I will try at the beginning, at least say some motivation why I will consider this type of metric, let's say. Okay, so the motivation is coming from a very simple and very nice theorem for compact Riemann surface, the orientation theorem. Let's say that any compact Riemann surface is a matrix of Gauss and Gauss curve. Essentially, here you work on the fact that to have a conformal structure is equivalent to have a complex structure, and you want to make a statement of that result in higher dimension. In Kähler geometry, I will review very quickly the Kähler case. The problem becomes to find a metric with special curvature property, like to have Kähler-Einstein, constant scalar curvature, whatever. In non-Kähler case, we'll see in a moment what I meant for non-Kähler. The problem becomes to study special type of Hermitian metrics. So metrics which are orthogonal with the complex structure, but there will be not anymore a symplectic structure. And I will focus on two types of metric, the balance and the pluricloss, which are also called in literature SKT, strong Kähler with torsion. I will explain a little bit why I have this name. Okay, Kähler case. The Kähler case, in some sense, one can see that the Kähler, there are complex manifolds that are more complex than the others. So the Kähler case, because it's a mixture between complex geometry and symplectic geometry. Let's take a complex metric. And I will say that the Riemann metric is J-Hermitian. If you have this compatibility, right, between the Riemann metric and the complex structure, so G is orthogonal with respect to the complex structure, J is orthogonal with respect to the metric. One can define in a natural way a form of type 1-1. This is also called the Kähler form or fundamental form, and you shall define that way. The nice thing here that when you fix the complex structure, to have a metric or to have the 1-1 form is equivalent, essentially. Okay, in the Kähler case, we have we said that complex manifold is Kähler if it has a Hermitian metric such that this 1-1 form is also closed. So it's also non-degenerate. So you have this mixture between symplectic and complex structure. Okay, so the example. Here, just review very few things, and I will point out the difference. So there are crucial difference in complex dimension 1 and complex dimension 2. Okay, for complex dimension 1, a 2 form is always closed. So all the Riemann surfaces are essentially Kähler. Very simple example of Kähler manifold are complex-oride. Essentially, the structure there comes from the flat structure. CM, then complex projective space, and more general smooth projective variety, so locus of homogeneous polynomial. Okay, it's very different the situation when you go in complex dimension bigger than equal than 2, because then you have necessary topological condition. One condition is the odd Betti number to be given, and then you have also restriction fundamental group. And we have also a restriction on the formality in the Sullivan sense, so in the sense of fractional homotopy. I will go back to this condition later in relation to the pluricloss metric. And B1, in the nice thing that for complex surface in the compact case, B1 is given a difference. So it's really, that's what's conjectured by Kodaira and proved by CU using the classification of complex surfaces, and then independently by Boukdal and Lamoury using currents. Currents in the sense using the duality between form, essentially the dual of form with compact support. And this is not anymore true in eigendimensions. So this makes different. Is a little bit nice. Okay, it's nice because we B1, you detect essentially if it's scalar or not. But on the other hand, there is a lot of work still in the classification of compact complex surfaces, especially in class 7. So the non-Keller case is still a mysterious in complex dimension 2. Okay. One motivation, especially for if you think about balance, come from, let's say, the Calabi-Yau condition. So let's start with the Calabi conjecture. Okay, when we have this compact Keller manifold, here I will identify the metric just with omega. So I will say omega, the fundamental form, Keller metric. And then if we use holomorphic coordinate, local holomorphic coordinate, omega is this expression in terms of this is alpha. And one has seen in the Keller case that the Ricci tensor is J-invariant. So one can define in a natural way the Ricci form, right? Which is just defined taking the second derivative of log of the determinant of the metric. This is, even if this is a local expression, is define a global form of Taiwan 1, which represent the first chain class up to this factor, 2 pi. And that was conjectured by Calabi. In fact, this year, I think it's the 100th birthday, right? Of Calabi, I think, if I remember wrong. Given a closed 114 representing the first chain class, then he conjectured that it's always possible to find a Keller form such that the Ricci or the Keller form is just E. And this remained open for 20 years, but then he solved that. And in fact, they show that if you start with a compact Keller manifold and you take any closed 114 representing the first chain class, then there exists a unique Keller form in the same Durham class. So the difference is just an exact form, such that the Ricci of that Keller form is exactly what they call them. Okay, this can be viewed in an eigendimension of the uniformization here that we saw before. And the very interesting case is the case when C1 is 0. Because when C1 is 0, you imply that the Keller metric is already flat. And then you get this example with one of the example with, let's say, holonomy is an SUN, right? You have all this theory about Calabi-Yau manifold, whatever. We'll see a generalization of that. And of course, it's the complex dimension. So after that, there was a great interest to extend this theorem in non-Keller setting. And one extension we'll see is related to the balance metric in relation to the Hallström system. We'll see how. Okay, so first thing that one can do, okay, one can try to generalize something in non-Keller, asking that just again a compact complex manifold and asking that the canonical bundle is holomorphically trivial. So that means that the complex dimension is n, you have a non-vanishing holomorphic n0 form. Especially complex dimension 3 was quite interesting. It's still quite interesting. And so one can ask, okay, let's take a compact complex manifold, which is Calabi-Yau in the sense that I wrote before, and which canonical Hermitian metric one can choose. Special type of, I say conformally balanced, because in fact you do a global conformal change of a balance metric. I will define what balance. And the motivation of that can be viewed that if you take the usual Keller Calabi-Yau, free falls, complex dimension free, then this can be viewed as a special solution of the whole Strominger system. So now I will save I will review something about balance, and then we'll go to the whole Strominger, and we'll see what is also my small contribution on that direction. But anyway, let's start with balance metric. What is a balance? That's definition is due to Michelson. And so let's take a complex manifold, dimension n. And this time we ask that omega is such that if you take the wedge power n minus 1 time, this is closed. So essentially you're asking that you have a positive close n minus 1, n minus 1 form. That's what you ask. There is a nice characterization in terms of the Laplacian with respect to delta and delta bar and del, I should say in English, del bar and the D. This is due to Gudshon. It shows exactly that equivalence. But the nice, I think the more maybe useful characterization is in the paper by Michelson himself, because that's give an obstruction. I will say which one. So Michelson showed essentially by duality, using the duality between the currents and the differential form with compass form, that a complex manifold as a balance metric, if and only if, cannot have any positive currents at degree 1, 1, which are component of the boundary. So which are the form, let's say ds plus d bar s bar. That's what he's asking. And that's given a structure. This is the only known structure that one knows. And if you have if your manifold as a balance metric, then it cannot have any complex manifold of codimension 1 homologous 0. That's obstruction. And for instance, this obstruction apply to Calabi-Ekman manifold, which are essentially the product of odd dimensional sphere. That's an obstruction that you can apply in that case. Okay, but there are, I mean, the first example probably was contained in Michelson in self paper, and that's it's quite natural because you start for a 4-dimensional oriented anti-self dual Riemannian manifold. So the W plus the self dual part, the Weil tensor is vanishing, and that condition ensure that if you take the twistor space, so the bundle of oriented orthogonal, almost complex structure, this is as a natural integral complex structure. So this is a complex structure, and that's, in that case, you have a balance metric. Another property, nice property of the balance condition, that if you start with a Kähler manifold and you apply just bimeromorphism or more general, that means that essentially you modify your manifold outside the thin set, let's say analytic thin set, then you still get a balance. So you go from there, so it's preserved by that condition. So natural manifold that you construct are Morrison manifold. These are bimeromorphic to projective manifold, and more general, the Fujiki class. These are bimeromorphic to compact manifold. But there are very simple examples that you can start, that you can construct from Lie groups. Just take a complex Lie group, a unimodular one, and so the complex structure is bi-invariant there, and just take any left invariant there, compatible, then is automatically balanced. So this is give the example of compact, complex, parallelizable manifold. But then there is also, I don't want to give many detail of that, but a very nice construction is due to Li, Fu, and Yao. And this is with Califold transition. So you start from a Kähler Calabi-Yau, And then essentially you apply this conical transition, which is a combination of you contract some rational curves, and plus you get something with a double point, a singularity. So you just do it smoothly, like the formation. And that was very nice because, for instance, with that construction, they construct at some point of balance of this type with K bigger than equal connected sum of this with K bigger than equal than 2. But the case, for instance, S3, cross S3, I would point out that we know that with the Calabi Ekman structure, the usual one, the compact structure, this doesn't have any balance. We know from before, but it's still open. So this simple example is still open if you can have in general a balance map. Other construction from more related to symmetric space is due recently by Jussi and Podesta, where they show that every non-compact simple group of inner type, that means that if you decompose the Lie algebra, your simple group like G, and then you take the maximal compact embedded subalgebra, and you decompose every Cartan subalgebra of the maximal compact embedded subalgebra is also Cartan subalgebra of the Lie algebra. So it's something related to the symmetric space. And in this case, you take any invariant complex structure there. So coming from the Lie algebra, you have that. Okay, now we will review something more related. This is, before to go to the Hallströminger, I will review some construction that I did recently in a work with Grancharov and Misha Verbitsky, Grancharov and Misha Verbitsky. This is related to the suspension of mapping torus. And in fact, in that case, we will go again from Kähler to something on Kähler. We'll see how. So let's take just the manifold and the hem and the diffeomorphism. So we just take, this is very easy to construct, you just take the product of hem times the closed interval, 0, 1, and then you identify the point P0 with, you use a diffeomorphism at P1. So if you take the natural projection on the second factor, this gives you the structure of fiber bundle with base S1, essentially in fiber hem. So this is also a cyclic group, right? The structure group. So you can view the same manifold as a quotient of M times R by the zeta action in that way. That's another way. And you get exactly the same. Okay, that's an important remark that will go later, a link with nil manifold and Sol manifold, when I gave also contribution. So if we take the length 1,4 on the circle and just do the pullback, this is a closed 1,4 on your mapping torus. And in fact, this is a theorem by Tischler. Anytime you can distinguish if your manifold is a mapping torus or suspension, if and only if it has a closed one form, which is non-vanish. That's a condition. So inside this family of manifold are included the nil manifold that were already mentioned yesterday, they told by Busol, and Sol manifold. So here a main compact portion of the group by Lattices. So what is known, for instance, in the Sol manifold case, when J is invariant, here one can use, this is a type of thing that is applied for the balance condition, but for many other type of Hermitian metric, because you just use that since G admits a compact quotient, then by minor result, you have a bi-invariant volume. So using that bi-invariant volume, any let's say lasting not invariant structure that you have in your compact quotient, using the integration by the bi-invariant volume, you can get something invariant. Okay, so in this case, if you fix, you have your complex structure, you assume that your complex structure is invariant, so it's coming from the Lie algebra. If you get any Hermitian metric with some property, Oh, sorry.
Yeah, are these dimensions complex dimensions or real dimensions?
Complex.
Okay, just.
But this symmetrization that I am thinking now I am doing with the metric, so with the 114. But in principle, you can do with parts only tensor, even in the real case. You just do the just by symmetrization, yes.
So dimension 6 would be real dimension 12. Right.
Yes,
Okay,
yes,
okay.
yes, yes.
Just reminding
yes.
myself, thank you, sorry.
So this is just with this symmetrization, they think that if J is invariant, so it's coming from the Lie algebra, then everything can be worked out at the level of Lie algebra, essentially. So there are some classification results. The first one is due to Ugarte in the important case. And then with Ugarte and Dutal, we work out in more. This is related to what we saw before with holomorphically trivial, because that's a condition to have a holomorphic free 04. So it's non-vanishing everywhere. So you have a holomorphically trivial bundle in that case for that Thorne manifold. And then more recently with my student Paradiso, we sort out essentially two types of solvable case, the almost abelian and the almost impotent. Almost abelian are very close to abelian, and the condition is quite strong, but I don't want to talk about that. But there are, we found that characterization and also classification. And there is also a nice construction written by Freiberg and so on. This is the something nice because they generalize the fact that if you work with two-step nilpotent or nil manifold, whatever, you can get by T-duality, by a twist from a torus. And here he extends that for the two-step solvable, essentially. This is called the share construction. Instead of using the action of the torus, is using just flat vector bundle. That's the idea. Two flat vector bundle with some property and blah, blah, blah. But I don't want to talk about that. But the nice thing that this share construction, that is something very algebra, let's say, is preserving the balance. So if you start with balance, it's again going to balance. Okay. Let's see what I get in the result that I mentioned. There was the motivation to consider special type of suspension that we call hyperbolic suspension comes from a paper due to Quinn and Wang, where they construct compact manifold, dimension 6, which are at the same time, okay, complex Calabi-Yau in the sense that I explained, they are non-Kähler, and symplectic Calabi-Yau. That means that the first chain class is 0 for the almost complex chain. So the problem, so they didn't look any metric problem in that construction. So we try to understand which type of canonical metric or Hermitian metric you can have. And so the natural question is, do they make a balanced metric? And we'll see that the answer is yes, because this type of manifold, in fact, belong to a more special type of suspension. I will say in a moment. So here I just review very quickly what is this construction by Quinn and Wang, the motivation. So they use the Kummer surface that you can view as the smooth compact surface. You just obtain in blowing up the singular point of the quotient of the two torus, right? T2 over T2, just by essentially the involution that is changing the sign, right? To the two coordinates, theta and W. And one can view also that the Kummer surface as a quotient of that type, where essentially how is the involution induced by the other? That's another way to see. Okay, what we can remark about that? The fixed set of this tau of this involution is the union, right? Or the sectional divisor corresponding to the singular points. But that's a nice thing, because if you take the zeta 1, where this zeta 2, which is a 2-0 form, this induces a nowhere vanishing 2-0 form on the top. And this pullback induces a holomorphic 2-0 form. So you have also holomorphic 2-0 form on there. And now we go to the suspension stuff. If we take a matrix okay, with coefficient zeta plus I zeta, but we determine 1. That you have an extra condition that the modulo of the trace of A is bigger than 2, and you ask that you have is diagonalizable with 2 eigenvalues. Okay, the one is the inverse, is just a condition about the determinant 1. And last note, but D1 and 2, they also say eigenvector of the induced metric at the level of the first cohomology. Then the induced metric preserve such form, and also the sum of the divisor, let's say. So you have a holomorphic transformation, the Kummer, preserving the induced holomorphic 204. So now you can do this thing. So you just take, you don't yet take the quotient. So you don't yet consider the Kummer, just take the 2 torus times R times S1, and then take this action. So B on the 2 torus, you have the action given by the matrix, and then you just translate on X, and you don't do anything on Y. This is sum to a compact quotient, and this is with still has trivial canonical bundle because everything is preserved, right, by the math. Okay, this allows to consider a more general class, let's say, of structure, because here we are not preserving any metric, so just a compact structure. So you start with holomorphic automorphism of a compact Kähler manifold, and we will say that is hyperbolic is the action at the level of cohomology, 1, real cohomology, as a unique eigenvector with eigenvalues lambda bigger than 1. That's the hyperbolic condition, essentially. Using that, one can construct what we call hyperbolic Tori suspension, and the previous case is exactly a special case of that. So what we do, you see, we have here. You can do more general. In fact, you can also do the same, taking 2 holomorphic automorphisms that commute. But in this case, 1 is the identity. So it's more general, the construction. And then the quotient that you get in that way, of course, is the from 1 to MS times S1, because the second one is just the identity in this case. And the previous case is exactly a special case of this thing. In the compact hyperkähler, if you take a compact hyperkähler manifold, so like the example before, so you have a Kähler and also holomorphically symplectic structure, and you take a hyperbolic automorphism, preserving the holomorphic symplectic form. Here, the only thing that we use that is preserve the volume, essentially. You only use, so it's more general, the statement that I am writing here. We show that such function is always a balance metric. So the previous construction as a consequence is a balance metric. The proof is more general because, as I say, we use the fact that you have this projection, see on the 2 torus, S1, S1. So it's a convex curve. And we show that, in fact, this is what in Michelson paper she called like essential holomorphic projection. That's what we use. I wrote down the construction in this special case, but as I say, it's more general. Just okay. One can start with the real 4 torus. If you start with the real 4 torus and you consider the same A matrix like before, what you get is just a whole manifold, just almost a million whole manifold. In that case, the metric is explicit. So it would be nice. Also, for instance, the previous construction, we know that there exists, right, the balance metric, but we don't know how to write the metric, how to find that. That's something that we are still working on that. Okay, so I promise that from balance we are going to the Hall-Strominger. Okay, here I will not talk about physics. I will just say a few words about that. But the idea, what is the compactification? So essentially, you go, essentially the length from 10-dimensional to 4-dimensional, and the 4-dimensional is a Minkowski space. So you can describe such type of heterotic superstring with a Lorentzian manifold. So you have something like MS. Oh, you're right. This is black is not good. M6. M6. No, this is not that. It's not. M6 times Minkowski. So it's just a product locally, of course. This is so is Lorentzian because here you have a Lorentzian metric, and this is compact manifold, and in fact is a complex Calabi-Yau manifold in general. And you have a vector bundle. That's vector bundle is holomorphic vector bundle, and the idea is to reduce all the equation that comes from superstring theory to the geometry here, and also to the gauge. The geometry related to the gauge bundle, E, let's say. Okay, so the first case that the first solution of the whole Strominger system, I didn't write yet the equation, but first I found out where it is coming out, and then we'll see what are the equations. Is due to Candelas, Horowitz, Strominger, and Witter in 85, and because on this type of product, you can have two types of metric, right? The product metric or the work metric. If you consider the product metric, then okay, you can take E, your bundle is essentially the holomorphic tangent bundle of your Keller manifold, in fact, because posteriori what happened that the sixth manifold has to be Calabi-Yau with the Keller case. And to find a solution of such system essentially is equivalent to give the Yau solution for the Calabi conjecture essentially. And then independently, Hall and Strominger consider the work. That's make the thing a little bit more complicated, because in this case, you still have the complex Calabi-Yau, let's say, condition, so the mild condition, not necessarily Keller. But of course, the problem is, okay, which type of metric that you have? You don't have the Keller condition, you have another type of metric. And the type of metric that you have is a conformal metric, globally conformal metric to balance, exactly, to the balance case. These are exactly the equation. So we start with a compact, so complex dimension free manifold with holomorphically trivial bundles. So we have an aware vanishing holomorphic from 0 4, big omega. And we take a complex vector bundle over here with a Hermitian metric along the fiber, and then we have a constant alpha prime. This constant has a physics role. From physics point of view, alpha prime has to be bigger than equal than 0. But in mathematics, the people consider also all the cases, even alpha prime negative. These are the equations. Okay, you here just a notation. You take H, this Hermitian metric, and then you take the Chern connection and the curvature. So FH, you think like a 1-1 form with coefficient in end of E, and the same for the curvature for nabla, the same thing. So it's 4. So the first equation is just the Hermitian equation. So the components of the curvature 2, 0, 0, 2 are vanishing, and the wedge with omega squared, here we are in complex dimension 3, is 0. Okay, this is I don't want to say much about that, but this is the stability, essentially equivalent to the stability of the holomorphic bundle that was introduced in geometric invariant theory. That was introduced for Keller manifold, but was extended by Lee and Yau for what we call Gouduchon metric, because in fact this metric is Gouduchon, so it is conformal to a Gouduchon metric. And I don't want to say much, but this is related to the stability of the bundle. The second equation is exactly the condition to be conformally balanced. The function is just the norm of the form, physical form, with respect to the metric. And the third one is the more difficult part. And this is the, let's say, distinguish the in that sense, is the canonical condition, is the curvature condition, like can be Keller-Einstein, constant scalar curvature. In this case, is of course a combination because it's involving the curvature of two objects, right? The chain connection on the holomorphic bundle and a connection. Here, there is some freedom about the connection. The first solution to the Hertz-Strominger system in non-killer case was done by Fu and Yao, and this was considering as connection the chain connection, the one for which the torsion is only the one part of the torsion is vanishing. But from physical point of view, the more interesting case from physics point of view is not the chain connection, but is what is called the bismuth connection, the one with, yeah.
So usually when people talk about stable orbital bundles, the slope usually refers to the degree of the bundle you might be passing away.
Exactly, the slope.
Here, your alpha prime is also called as orbital number is alpha prime. You also call it slope parameter has a different meaning. This is alpha prime.
Yeah, there is a different meaning with alpha prime. Yeah, the condition about stability is true. It's about that the slope is related to what is called the slope. So the degree over the rank. But alpha prime, in principle, the only restriction in the equation you don't have a restriction. Alpha prime can be unreal, but as I say, from physics point of view, alpha prime has to be positive. Of course, alpha prime 0, then you get the Calabi-Yau condition, Keller Calabi-Yau condition. So, yes, yeah. So in that sense, you can consider that as a canonical metric. As I mentioned, Calabi-Yau Keller manifold can be used as a special solution. You just take the holomorphic vector bundle, like a holomorphic tandem bundle, and H is equal to omega in that case. So alpha prime is 0. So then we know that case. When omega is non-killer, then you have a one parameter. You can choose many Hermitian connections. These belong to one parameter family. This is a result du show. You have this family, which include the chain connection and the bismuth connection. Now we'll consider the chain connection. This is exactly the connection considered by Fu and Yao as when they consider the first non-Keller solution to the system. This is, I will review a little bit because we generalize that using the Goldstein and Prushkin solution. This is a generalization of the Calabi. You probably pronounce better than me, as I am very bad today with the pronunciation. This is a generalization of the Calabi Heckman conception that I mentioned before. There are also non-Keller solutions, only groups. For instance, Fernandez, Ivanov, and Huarte construct a Near manifold, in the compound, sorry, and Fei Yao constructing on complex polarizable, in fact, manifold. There are also solutions, and there is all the theory related to the duality, but I will not mention by Garcia and Fernandez. They constructing also that. And Fei and Wang and Picard, they construct also solution when the base is a compact answer, and the fiber is compact hyperkine. But let's go to review the construction of Goldstein and Prushkin, and let's see how we generalize that. Okay, let's start with a K-free surface with, I will denote by small omega, yes, a Ricci flat Keller metric. Okay, now we need, the first thing is to construct the T2 bundle, right, over your K-free surface. And this you do choosing essentially two pair of 114, which are anti-cell dual, and which represent up to factor 2 pi, an integer curve. And then the Goldstein and Prushkin associate the toric fibration. Essentially, the compact structure here is constructed in such a way that the reaction become holomorphic. That's the idea. And theta are the connection of. Okay, so d theta is just a pullback under the projection of omega I. Okay, what was the original conception by Goldstein and Pushing is the following. If you take the pullback of your Taylor metric down, and you just add, okay, the vertical direction, so E, theta wedge, theta bar, you get the balance. So the wedge of that is just closed. What I did for now is to modify that part that I mentioned by scalar function. So you see, instead of considering omega s, you just consider a scalar function, exponentially do, or use a function. Here is just a condition about the positivity of the method, because it's not enough, of course, to modify that. You need also that the one form is positive. That's exactly the condition, plus an average condition. Okay, what we did with Grancharov and Bezzoni is okay. Instead of considering a K-free surface, let's consider K-free with singularity, with Duval type singularity, so cyclic isolated singularity, a K-free hard before, and we extend the result by Fuyao in that situation. I will not mention how we prove that. I just mentioned one thing. What we use essentially that the solution by Fuyao as let's say the construction is working because you have what is called a Calabi-Yau foliation. So in fact, it's depending only on the twisted Calabi-Yau foliation. So what we use is to reduce the equation. We will not have any more a complex Monge-Ampere equation, but we will have a twisted, let's say, complex Monge-Ampere equation, and then using some result that we know about transversal elasticity by Kachimi, we could solve the equation. And the idea here that we construct, this is a final, in fact, is a corollary of the construction, but we construct new solution for the Hall-Strominger system, which are essentially given. Okay, the first solution are not simply connected. You have a product with S1, but the second family, the connected sum are type of S2 times S4, and connected sum R plus 1, S3 cross S3, simply connected. So these are new simply connected solutions for that, which are mid balance, and this is, and for K equal to 82 or equal to 282, you just get the Fuyao solution. So in that sense, and our student is working now in possible generalization because we consider only one K-free orbifold, and to see if I can consider more, and also to see if you can go to one to the other after you construct, if you can move a little bit from one to the other, because there are not so many. But this is work in progress of the student.
So the restriction on this K and R are used to what? I mean,
no, here essentially this K and R are doing because you do partial blow-up of your complex K-free orbifold. So you do using this partial blow-up, you construct still something which is singular, right? But then we construct on every step, let's say, a T2 bundle. I will explain in a moment how is constructed a T2 bundle, a little bit, not much, but a little bit. So let's say S is the orbifold, the K-free orbifold. What we consider choosing special type of divisor with partial blow up, we consider what this safer S1 bundle generalized safer S1 bundle in dimensions 3. So the idea that you have this map, in this case, you have a map over a complex orbifold, right, which is with fiber S1, and this is this construction, safer S1 bundle was very useful because was used by Boyer and Galiski to construct Sasaki-Einstein structure. So it's very powerful due to color, and we adapt in that case. So the idea that we constructed a thing, first considering going from N to M1 with a smooth paper as one bundle. You can construct the fact that it's smooth using color theory, essentially. And then the other one is just a regular principle as one bundle. Of course, we could identify topological the six manifold because this manifold are special type. Are simply connected, you have this locally free S1 action, so you can use the topology to identify the spacing. Okay, I have, I think, 5 minutes. Yes, it's correct. Yeah, maybe 10. Yeah. I don't want to destroy you, so it's you are not. But I promise that I was talking also pluriclose, and we'll see a link between the not a link really, because it's not clear if you can have both structure. Anyway, I mentioned the bismuth connection without defining it. This is now they call bismuth connection even in the non-Hermitian case. Just you have a connection, a metric connection, and the torsion is close, essentially. Using the metric, you can think your torsion as a zero free tensor, and you also the skew symmetry in all direction. In this case, in a Hermitian case, the difference between bismuth and left theta is just given by the data. So you can see from here that you can ask for a special case. So when the bismuth connection is closed off, that means that this is omega 0, and equivalently means that omega is d-bar close. That's what is called pluriclose, was called pluriclose by Stritz and Tian, because they also introduced a flow evolving this type of Hermitian structure. Of course, in the Kerr case, the bismuth is just the Levishivita, and that's exactly the condition. Pluriclose in the sense that it was omega, but previously from physics was called strong Keller with torsion, but there are too many things with torsion, so maybe it's better to use now pluriclose. This is there is, you see, in any dimension, complex dimension n, there was for complex dimension 2, the period one just a special case of what is called Goudouchon. Goudouchon metric are, let's say, to have a Goudouchon metric is quite easy for compact Hermitian manifold, because it was shown by Goudouchon that if you move in the conformal change, then you can find such metrics. So in complex dimension 2, to have pluriclose metric is easy. Let's say you just do a conformal change, then you do, right? But that's not the case in complex dimension 3, at least. That's completely different, the situation. Okay, example. Example are the more trivial example are even dimension compact real group. They give you just take the J, the complex structure, and you buy invariant. Then it's giving a pluriclose. But in this case, the bismuth connection is flat. So if from that point of view, it's less interesting. And then there are examples in the class of mean manifold. I found out with Salomon, for instance, we consider the complex dimension 3, and then I mentioned them more recently. Arroyo and Collini also work on that. There are examples on Sol manifold, and there are also, these are very nice constructions. We do Mitigrancio, Gegrancio, and Pon, because again, it's involving connecting sum of k minus 1 S2 minus 1, connecting sum k of S3, S3. I just mentioned that that is a special case of, again, a construction of T2 bundle over Kerr. So you can see from here that many of these type of construction, manifold, whatever, are constructed by using torus bundle. That construction was generalized by Pollard and Kapoor, considering principal bundle over projective manifold and changing the structure group on that type of Lie group. Okay, now I just say a few words about the interplay between the two types. So we consider balance and we consider pluriclose, right? Okay, one thing that's not complicated was proven independently by Alexander Ivana and Popovici. If you have balance, so the same metric, you impose balance and pluriclose, this implies carrier, so you cannot have. With Vezzoni, we did this conjecture. Now is some here that we did this conjecture. So we conjecture, okay, every compact complex manifold which has a balance and a pluriclose, so different, of course, then is automatically clear. This until now, nobody disapproved this conjecture, so it's still on. And even the constructor that I mentioned at the beginning, that's what's hard, well, not so easy. This suspension stuff, the hyperbolic suspension, we prove with Gracher and Verbitsky using currents that they are balanced, but not pluriclose. And the proof with currents is a little bit technical, but we succeed. So it's again using current. Many results are non-existent. For instance, the twistor space, Verbitsky showed that you have a balance, but not the pluriclose, again, using currents. So the characterization that you can have using currents are very powerful method, but in other methods are any type of manifold, compact complex manifold that you try to show, if they are balanced, they are not pluriclose, essentially. But there is maybe there is some obstruction coming out. There was, for instance, conjecture by Popovici about the degeneracy of some spectral sequence, but it seems that is not frolicker. It seems that it's not working. I mean, they found out contre-example, so we don't know if there is some restriction. In the non-compact setting, there are contre-examples. They just construct two-step solvable Lie group, which has one balance and one pluriclose, and they are not killer, essentially. So that's so in that case, okay. I think I finish here. Probably there was a part about generalized geometry, but I don't want to explain. If there was time, then I was explaining. But I think it's a good time to stop here. And thank you very much for the attention. Yeah, thank you.